The principle of equivalence is the principle that guided Einstein in his search for a relativistic theory of gravity. That theory of gravity, the one he constructed at the end of this search, is what we call general relativity. However, this equivalence principle didn't come from nothing. There was originally a simpler version of it called the weak equivalence principle. The one that he used is now called the medium strong equivalence principle or Einsteinian equivalence principle. In order to arrive to this formulation of the medium strong equivalence principle, it is convenient to start by reviewing the weak one. And this weak one comes in several formulations itself. For instance, it is called Galilean equivalence principle, principle of universality of free fall, principle of equivalence of inertial and gravitational masses, and okay, basically the first and the third are the same formulation and they just different names. Okay. Now, in order to review these formulations, the different formulations, we have to go back to Newtonian physics and revise some notions that we have accepted without discussion in more basic courses, like those of mass, the different kinds of masses that really appear in equations of physics that we just describe with a single parameter. Okay, so there is first the notion of inertial mass. Say that we are always talking about a particle. This inertial mass that we are going to denote by mi is just the quotient between the force and the acceleration, the force applied to a particle and the acceleration that it is produced. Okay, basically the same definition appears in special relativity, not just in Newtonian physics. Then there is the active gravitational mass. That we are going to denote by mgA. Okay, it is the one that sources the gravitational field. So for a particle and using Newton's universal law of gravity, we know that the field G is given by minus the Newton constant, and then the mass that appears here should be the active gravitational mass. Okay, and this is R divided by R cubed. Okay, there is a second gravitational mass that obviously will receive the name of passive gravitational mass, and that we will denote by mgp. All three refer to the same particle. So this is the gravitational charge of a body, or the force that it suffers when it interacts with a gravitational field. G is proportional to this mgp. Okay, so this would be the formula that effectively or implicitly defines mgp, if this is the gravitational field intensity. Usually we don't distinguish between these two. Okay, we also distinguish between these two and the other one, but never, certainly. Maybe you have had a discussion already of the equivalence between inertial mass and gravitational mass, but probably nobody mentioned the possibility that there are an active and passive gravitational mass. The reason why is because if you apply the third law of mechanics, the principle of action and reaction, you arrive to the conclusion that they are equal, and we can see this in this way. Suppose that there are two bodies which interact gravitationally, and they have gravitational masses mgA1 and 2. These are the active ones, and passive gravitational masses mgp1 and 2. Okay, let's focus on the force suffered by the particle 1. This could be F1, and then we apply the definition of passive mass, so this would be mgp1, and the force sourced by the particle 2. Now this is, according to this definition above, could be mgp1, and this is times minus gn. Now it is the active gravitational mass of the particle 2 that comes into play, and this could be R12, okay, or rather R21 divided by R21 cube. Okay, and let me put everything together. So this would be Gn mgp1 mga2 R21 divided by R cubed to 1. Okay, so R21 originates in 2 and goes to 1. Okay, if I do the same and I study the force suffered by the particle 2, it is clear that I will get minus Gn, and everything interchanged, interchanging everywhere, M1, sorry, the indices 1 and 2. So this would be mg2, mp2, and mga1, and now this would be R12, and here R cube R12. Now the principle of action and reaction tells you that F1 is equal to minus F2. Okay, we know that R12 is also equal to minus R21. So you put everything together, you arrive to the fact that the conclusion that mgp1 mga2 is equal to mgp2 mga1. So now if we divide by mgp1 here and by mgp2 here, then we get mga1 divided by mgp1 equal to mga2 divided by mgp2, and this is a universal constant for any particle. The quotient between its active and passive gravitational masses is always the same. One can always absorb this constant k. So let's say that we decide that we want to express everything in terms of passive masses or gravitational, or okay. So yeah, the passive masses. Then for any particle, you would replace the active one by this times k, and in this definition, okay, here is where mga would appear. You would have k and mgp r divided by r cubed. Okay, now you redefine the Newton constant, and you from now on you always use the passive gravitational mass everywhere, and this is basically what we are doing every day. We only use one gravitational mass, and equivalently we can say that we are using units in which both are identical. So from now on we eliminate the subindex A, the subindex P, and the prime in Gn. So we take these two things and we only talk about inertial mass and gravitational mass and the Newton constant, which appears in this formula. Now, as you know, Galileo performed a series of experiments with inclined planes, letting balls of different compositions roll over them, and he concluded that all bodies of any composition fall with the same acceleration g in the proximity of the Earth's surface and the effects of gravity. Now this G is applying the second law of dynamics, the portion between the force, the gravitational force, and the inertial mass, this for any particle. And this force is the product of the gravitational mass of the body and say the gravitational field, intensity of the gravitational field, which is, well, defined basically as the quotient between the force and the gravitational mass. If this is this is the same for all particles, okay, it's a property of the field and created by the Earth. This is also the same for all particles as a conclusion of the experiment. So this is experimental. Then the conclusion is that the quotient between the gravitational mass and the inertial mass is some universal constant that, okay, we can call K prime. And we can replace everywhere now the gravitational mass by the inertial mass using this K prime that we can absorb again in a redefinition of the Newton constant, and then we can write both the second law of mechanics in terms of the inertial mass and also the law of gravity. So if only the inertial mass appears, the weak equivalence principle can be viewed as a more precise formulation of the Galilean equivalence principle that applies not just to the surface of the Earth but to the entire universe. It talks about the gravitational acceleration that is suffered by particles, but the particles which it refers to have to satisfy two technical conditions. Okay, the first condition is that these particles are test particles. I have already mentioned test particles, but now we want a more precise definition of what they are. And these particles have to be in free fall. Again, there is a precise definition of what free fall means, and I am going to give it to you now. So first, test particle. What is a test particle? Okay, it is a body. The body that satisfies several properties. First of all, it is electrically neutral. So electrically neutral, which means that it has zero charge. It means that it will not feel electromagnetic fields, but also you know that an electric charge, when it is accelerated, radiates electromagnetic radiation that also back reacts on the motion of the particle. We don't want that effect to take place here, so we demand that these particles are electrically neutral. A second condition, which is less obvious, is that its gravitational binding energy is gravitational energy, binding energy is much smaller than its mass, or than the energy related to its global mass. So what is the gravitational binding energy? Okay, we can think of a massive body as composed of different pieces. So you can take one of the pieces, bring it to infinity, and then let's think on putting this piece back. So you let it fall in the gravitational field of the rest of the body. It gains kinetic energy, and this kinetic energy that it gains, if you remove it somehow, is the same energy that you have to give it back to separate this piece and bring it to infinity again. Okay, this is the gravitational binding energy of that piece of the body. Now you think of all the infinitesimal pieces in which the body can be divided into, and sum of all those gravitational binding energies is the gravitational binding energy of the body. And you want this energy to be much smaller than the energy of the mass, because okay, it is not so clear now that this can happen. But if you think of energy as the source of the gravitational field, as we have discussed, the principle of special relativity tells you that energy will be a source of a gravitational field. There is a chance that this kind of energy, gravitational binding energy, feels gravity in a different way than the energy which is related to mass. Okay, so we don't want this possible effect to affect our the formulation of the principle. So we assume that this gravitational binding energy is very small. Well, the gravitational binding energy of a body like the Earth is already big. Okay, much smaller than the mass, but it is sizable and can give rise to effects. So this tells you that the bodies you have to consider as test particles have to be small. Another property that we want is that they don't spin. These bodies don't spin, and this is because we know that the spin can interact with the gravitational field. Okay, this is probably even too advanced for this course. We will not see exactly how this happens, but the spin of a body modifies the gravitational effects that on that particular body. So we don't want that. And finally, we want that this body is small enough so suppose that the gravitational field is not homogeneous. So these inhomogeneities cannot affect in different ways different parts of the body. So in a sense, the body will be small and will almost only sample a region of space in which the field is approximately homogeneous. In this, if this is not the case, well, the motion, the body will start spinning, or there will be other effects, okay, because the forces in different places, parts of the body will be different. We don't want that either to happen. So a test particle is one that meets all these conditions. Okay. The point particles that we have considered in the past are similar to this. Well, before we added an electric charge to these massive particle actions, okay, they were electrically neutral. They don't spin. There is no degree of freedom that describes the spin. Certainly, they are point-like, so they are very small, and there is no gravitational binding energy for them whatsoever. Okay, so they were test particles, but the test particle is more general than the particles that we have considered so far. How about free fall? Okay, now free fall refers to motion. This motion under the Soule effect of gravity. Okay, so if you throw a stone, well, its motion when you release it from your hand could be free fall, whether it moves upwards or forward or whatever, but it is not a perfect free fall because there is friction with the air. The motion of a satellite is free fall if it has no rockets that acting on it. It will only feel the effect of gravity, so it is in free fall. So the word fall induces you to think that this kind of motion always refers to something that moves towards the Earth or the Sun or something like that, but this is not true. Objects which are in orbit, all planets are in free fall. So this is the definition. Okay. And now, with knowing what we mean by by a test particle and free fall, then we can formulate the weak equivalence principle, and it says that all test particles in free fall move exactly in the same way. Okay, this means same accelerations. Okay. So it is only the same motion if the initial conditions are also identical, and this may or may not happen. So if you look at what happens in the International Space Station, you have astronauts and everything moving in free fall, all of them, unless they touch the walls of the spaceship. They move in free fall, and what happens is that all of them move in exactly the same way. If you release many things inside of the International Space Station without pushing them or anything, so their initial conditions are the same, they stay together along the orbit. This means not that they don't move. It means that they all move in exactly the same way. This principle has been tested in many different ways. Observe that one of the important things is that the test particles could be made of different materials, and this principle does not even mention the material, so this should be valid for any kind of material. So people think that if it is not satisfied, it could be restored by assigning the different motions of the particles to maybe a fifth force. Okay, so checking the validity of this principle experimentally has also been interpreted as a search for a fifth force of nature. Okay, well, in the past it was tested by Galileo with inclined planes, by Newton with pendulum, by Edbos and other people with torsion balances. Also, it has been tested by letting things fall in a vacuum. Okay, and if you want to detect a difference between inertial and gravitational mass, you could parameterize the difference by this parameter. So you could say that this is this eta. Eta measures the difference between inertial and gravitational mass, and that this eta maybe is a property of the material. Okay. Now, if you study the acceleration of a body in a gravitational field, remember that it will be given by this, the gravitational field produced by a big mass m. The best way to detect an effect is to measure the difference between the accelerations of two different bodies. So they consider body 1 and 2 with the gravitational masses 1, oops, not a half, but 1 and 2, and 1 and 2. Okay, so if you now measure the difference between their accelerations, this is approximately eta 1 minus eta 2 gm r divided by r cubed. So this is what you can measure by letting things fall in the gravitational field of the Earth or the Sun. And what has been measured experimentally is that the difference for different materials of eta 1 and eta 2 is smaller for any kind of material than 10 to the minus 12.